As we move further into Module 3, we continue our discussion about quadratics and polynomial functions. So we've already learned about the quadratic formula, but there's a special part of it that has some significance. So the part underneath the square root, b squared minus 4ac, has a name. We call that the discriminant, and the discriminant will tell you the types of solutions or roots that the quadratic will have. So if I have a 0 that comes out from b squared minus 4ac, it comes out to be 0, that means I'm going to be square rooting 0, and the square root of 0 is 0, so it has a solution. But what that's going to do to the graph is give you one double root where it bounces off the x-axis, so it hits it and then just goes right back up. That would be 1, 0 with a multiplicity of 2. So anytime that you have a discriminant of 0, you'll have a 1, 0, one real root with a multiplicity of 2. If that value was a positive number that's not a perfect square, like 37, when you work this out and get 37, you're going to be taking the square root of that, but the square root of 37 is not nice. So if the discriminant is 37, it would be a quadratic with two real irrational roots. If that number was a perfect square, like 9, then I would be getting a nice square root. So the square root of 9 would come out nicely. That ends up giving us two real rational roots. So if you don't remember the difference between rational and irrational, rational numbers were things that could be turned into a fraction. Irrational numbers were things that just kind of have a decimal that goes on forever without repeating. So something kind of like a square root. So if we have an answer that has a square root in it that doesn't simplify, that's an irrational root. Lastly, if we have a negative number for the discriminant, like -4 or even -7, doesn't matter if it's a perfect square or not. Any type of negative would be an imaginary root. So we'd have two imaginary roots because we're taking the square root of a negative, and that automatically makes an imaginary number. So let's look at a few examples. We have this quadratic here, and we just want to figure out the discriminant. So I'm not trying to work out all of the quadratic formula. We just want to figure out this little section. So if I plug this in, I'd have b squared minus 4ac. And if we work that out, let's see, -1 squared minus 4 times 5 times -6 comes out to be 121. So the discriminant is 121, which is a perfect square. Its square root is 11. So this would mean that there are two real rational roots. It's not going to be irrational because the square root of 121 is going to come out nicely. For number 2, same situation. We do b squared minus 4ac to get our discriminant. So this would say 8 squared minus 4 times a times c. And we work that out. So 8 squared minus 4 times 7 times 5 is -76. Because we got a negative, that's automatically telling us we have two imaginary roots. For number 3, we do the same thing. So b squared minus 4ac would be -6 squared minus 4 times 1 times 9. And we just plug that into our calculator. But I get 0. That's okay, we can get 0, but what that tells us is that we have one double root. So it's one real root with a multiplicity of 2. And the last one here, 2 squared plus 7x minus 6. All right, b squared minus 4ac gives us 7 squared minus 4 times 2 times negative 6. That comes out to be 97. And if you don't know your perfect squares, that's something really to practice, but the square root of 97 is not going to come out nicely. It just is an irrational number. So because we get 97 for the discriminant, that means we have 2 real but irrational roots. So knowing the discriminant will help tell us a few things about the graph of it before we ever try to graph it. And for our class, we don't have a graphing calculator or Desmos all the time, so we're not going to be able to just know what the graph looks like automatically, but we are able to describe key features with our algebra skills. And 5 and 6, we're just going to try to solve these with the quadratic formula. So the first thing I noticed with 5 is that we have a quadratic where it's not equal to 0. So I'm going to move things over so that it is equal to 0 because I like a positive x squared. So if I add x squared to the left, that has something to combine with. We can add 4x to the left as well. But we also have to add a 23. And there's no other constant term on the left side. But that would give us 2x squared plus 12x plus 23. And now it's equal to 0. We're going to do our quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4 times a times c. And every time I'm thinking that out loud, I'm just filling in what are those values for a, b, and c. All right. Now that part underneath the radical is that discriminant. I always try to find that before I try to put this in the radical. So 12 squared minus 4 times 2 times 23 is negative 40. That clue right there, that negative, tells me automatically that there's going to be an imaginary number. So that, let's go ahead and rewrite that as negative 12 plus or minus I square roots of 40 over 4. But if this can reduce, we want to reduce it. And I know that the square root of 40 can reduce because 4 is a perfect square. So I could pull out that square root of 4 and make it a 2. But if you are still using your calculator, you'll get 2 square roots of 10 for the square root of 40. What that does is tell us that this is negative 12 plus or minus 2i square roots of 10 divided by 4. And we can reduce this fraction. We reduce the 12, the 2i, and the 4. All those can be reduced by a factor of 2. So I'm just dividing everything by 2, but I'm not dividing the radical by 2. That whole thing is being divided by 2, which means that the 2i is what's reducing. So that ends up being negative 6 plus or minus I square roots of 10 divided by 2. That gives us a little bit of practice with the quadratic formula again, but the only big difference is that now we have it where we have complex numbers or imaginary numbers. All right, number 6, we have x squared plus 36, but there's no middle term. There's a 0x there, so that's our linear term. If we were to work this out with the quadratic formula, it'd be negative b, but negative 0, plus or minus the square root of b squared minus 4ac all over 2a. And so we work that part out. Let's see what we get. 0 squared is just 0, but minus 4 times 1 times 36 is negative 144. So the square root of negative 144 over 2. That negative already tells us that we're going to have an imaginary solution, so we can even circle it or highlight it. But I get plus or minus I square roots of 144 over 2. I just kind of left the 0 out because 0 plus anything is not going to change, so it can be still the plus or minus there. But I can simplify the square root of 144 because that's a perfect square. So that's 12, which makes that 12i on top over 2. And we can simplify that 12 over 2 to just plus or minus 6i. All right, so this next thing is going to be about just kind of graphing something that has complex roots. So this review above, you can look back at that, but that is just showing us how to get something back in vertex form. So if we have this general equation, this is x squared minus 4x plus 9. We want to find all of our key features, and we follow the same steps we've been doing. So if I want to find the vertex, I'm going to do negative b over 2a. In this case, negative b is going to be negative negative 4 over 2 times 1. So I end up getting a positive 2 because that's a positive 4 when you do negative negative divided by a 2. That is not the whole vertex, but that's part of the vertex. It gives us the x value. If I want to find the y value, then I need to plug 2 in. So that would say 4 minus 8 plus 9, and you get 5. But you can put that in your calculator if you just want to double check yourself. So 2 squared minus 4 times 2 plus 9 gives you 5. So there's the other component of our vertex. There's the y value. This is going to open up. And I know it opens up because of that leading coefficient. That leading coefficient was 1x squared. It's a positive value, so it goes up. Our axis of symmetry is always x equals, but it's x equals 2 in this case because that's the x value of our vertex. And then I can plug this straight back into vertex form. So vertex form will say y equals a, which is 1. So 1 x minus 2 squared plus 5. You don't have to have that 1 there, but I'm just writing it to remind ourselves where it came from, that a value. Our y-intercept, we've got to plug in some of these things. So let's find f of 0 for the y-intercept. That would be 0 squared minus 4 times 0 plus 9. That's 0 minus 0 plus 9, which is just 9. Now, if you remember, we've talked about when it's in standard form, it's nice because you can just see the y-intercept at the end. But if it wasn't in standard form, if it was already in vertex form, like this, we'd still have to plug in 0. All right, the last part is finding these x intercepts. So let's think about this. It would mean we want to know when a function equals 0, x squared minus 4x plus 9, and it will not factor. If I tried to factor this, I'd be looking at what are some factors of 9, like 3 times 3, but that's not going to give us a 4. Other factors of 9 are 9 and 1, but that's still not going to give us a 4, so it won't factor. But I can do the quadratic formula, which is negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. And so we simplify just a little bit at a time. So underneath that radical, that discriminant is going to be negative 4 squared minus 4 times 1 times 9. Ends up being negative 20. That negative, there's your clue that there's going to be an I value. So a negative 20 gives us the I, but just the square root of 20 would reduce to 2 squared to 5. So what that tells us is that we have 4 plus or minus 2i square roots of 5 over 2. You've had a lot of practice now simplifying radicals, so that shouldn't be as difficult going forward. But the new thing is that we're just bringing the I part of it out. If I simplify this one last time, 4, 2, and 2 can reduce by a factor of 2, so I just get 2 plus or minus I square roots of 5. Those are the two solutions for that quadratic, or the two X intercepts. Two plus or minus I square roots of 5. These are our complex roots. That means that it's not going to show up on our graph. So if I go to graph this, I'm going to have, here, let's make the x-axis a little bit more obvious. There's our x-axis, here's our y-axis. But I have a vertex at 2, 5, so I'm going to go right 2, up 5, 1, 2, 3, 4, 5. And I know that it's going to open up. So that means that our parabola looks like this. Based off of our transformations, we've learned about this before, it doesn't have a vertical stretch, it's just a stretch of 1. So I'm going to go out 1, up 1 from the vertex, then out 2, up 4, because 2 squared is 4. We've talked about this before as well. So out 2, 1, 2, 3, 4. Out 2, 1, 2, 3, 4. We could have also found that the vertex, or sorry, the y-intercept was 9. So there's another point that we already knew without having to know our transformation. But there's our general graph. Notice it doesn't cross the x-axis. That's why we have imaginary roots for this. All right, in the second video, we'll talk about how do we factor higher degree polynomials.